Alright, time for another draftphysics.com, debatephysics.com also, but you just can't create any kind of interaction between people. So I've gone to forums and tried, fail. They will not, physicists, people interested in science, will not discuss anything foundational or elemental. We must believe what they claim, or there's no conversation. So you have to believe it's wave-particle duality is the explanation. It is of both things, and there's no determinism because nothing is ever in a place, and nothing's ever in a time, and nothing's ever real. And if you don't believe it, all right, they just won't engage at all. They'll just walk away. And they'll lock you out. They'll walk away after they close the door and lock you out. So again, I was kicked off of Wikipedia in 27 hours, and I didn't even edit a page. Just made suggestions. Just suggested they were wrong about something. Can't do that. So anyway, you just can't get anybody interested in these foundations of physics kind of discussions, and I find it frankly surprising. I didn't think everybody on the planet was a fucking asshole. I really thought there were some people that sincerely thought about things and, were interested in the truth. And no, they're just interested in pushing their agenda, and their agenda is usually based on some pile of crap that they've accepted over the years, and they're not going to let go of the crap. Ugh, it's just pathetic. Anyway. So there's this other video it's on a playlist of these older videos. It's obviously not one of the older videos. It's only 12 years old. It's not from the 60s. So anyway, but it does have some interesting shit in it. And so we're going to play it. Photons still, and double slit stuff, sort of. And you can just, it's just this selling. So it's called ViaScience, and it's just, this sell, silly shit. And so just try to show people the evidence in just the right way so you can make this goopy, silly, mush, crazy, nonsense crap make sense. And it doesn't make sense. It's still shit, and then if you think about it, you can figure out all the nuances of the shit. What's in there. Oh God, it's just so bad.
Welcome to the second video in this series on quantum mechanics. In the first video, we saw that classical physics failed to explain the relationship between temperature and electromagnetic radiation.
All right, so that's a silly way of saying, oh, there was some Raleigh Jeans catastrophe. There's no infinite amount of energy. Yeah, there's no infinite amount of energy. Yeah, okay. I mean, that's not a real reach, really. All right, so I'll try to explain. This is this whole ultraviolet catastrophe, blah, blah, blah. And it's all based on some idea. Okay, obviously something causes the photon, and the idea is the movement of electrons has something to do with it. All right, and the simple argument is you could just say it's a vibration. All right, and the argument is that, well, they're saying, well, there should be just as much infinitely fast vibrating as there is really slow vibrating. Like somehow we should expect them all to be equally easy to cause. So somehow causing a really fast vibration is supposed to be just as easy. That's what classical physics says, right? And classical physics doesn't say any such thing. And then when you understand it thermodynamically, okay, then you can sort of get this idea that, okay, thermodynamically, we're already, even when you're very cold, you're very warm, So it's just sort of a canard not to realize that all the average motion in the universe is, say, at some level. That almost looks too bright, but we'll see. No, that looks okay. So you have an average level of vibration. So let's just call that 50 cycles for the hell of it, right? So we could say that that's if you took all the stuff jiggling in the universe, the average amount of jiggling would be 50. And so, you could argue that, you'd have lots of stuff moving slower than the 50, because this bangs into this when they're both going this way, and, they lose energy. Like one's going this way and one's going that way, and, so you can understand how you could have places where it's going to be a lot less than that, and places where it'd be a little bit more, but there'd be no reason to think it could be infinite. So the idea is that, yes, the chart goes something like, this, okay, in reality. In terms of frequency or vibration speeds. So you could argue that, the average heat of the universe would be something like here. And so you're saying, yes, you can have stuff that's colder than the average, and you can have stuff that's warmer than the average, but that's about as far as you can go. You can't go anywhere. You can't extend this range infinitely. Okay, there's no infinite this way. There's a zero, zero vibration. So we know there's a finite ending here, and why would we think there wouldn't be a finite ending here? Why would we think it goes infinitely faster and faster and faster and faster, even though there's no mechanism to make it go any faster? Okay, except the mechanism of collisions and adding two things and causing an effect, in a constructive or a destructive. So this is sort of about constructive and destructive, right? Because we could say when the energies are constructive, that is, this is going this way and that's going this way, and the momentum of this is more than the momentum of that, it will give it more speed. So a light thing bounces off. You throw a ball at a moving car. So there's a moving car. You throw a ball at it this way. The ball comes back faster than you threw it because it takes a little bit of the car's energy. See? So your reflection is more than what you put in because this is moving. So the idea is that in a system you can make something hotter because you have something colder, but it's more massive. All right, well, anyway, there's probably better ways to illustrate the point. I think the car thing works in terms of understanding why you can increase a frequency or a velocity. And so the why was this expectation? There should never have been this expectation that it goes infinitely and it's just as easy to create, say, a X-ray as it is to create a infrared photon or a radio photon. That they're all the same amount of ease to create. There's no reason to think that, so there really wasn't any catastrophe. There was just this idea that, yeah, it's got to taper off. I mean, it's not going to be just some point, oh, it can't go any higher than that. No, it's going to taper off, and eventually you'll can't make more energy out of the heat in the system. The cars aren't going fast enough to have a reflection that causes, one of these. So you get a little bit of X-rays, and you get a little bit of gamma rays, and you get a little bit of these, higher frequency photons being created randomly, or out of the probability of a system, but very few, because it's a very unlikely event that causes one of those, and it's a very likely event that causes this infrared stuff. All right, anyway. Probably a big, longer explanation than I wanted, but okay. All right, since I'm drawing, I probably should just do the whole. So there's lots of different ways they attempt to describe this idea that you need a minimum amount of energy to cause electricity, and that's usually how we detect photons. So this sort of gets to the photoelectric effect, and they're telling a story about what it is, and I'm saying that now the story is even simpler, in that it's as simple as a tipping point argument. We know, physics thinks okay, that electrons are orbiting, doing all kinds of fancy stuff, but no, they're really in positions. And they're in positions related to the fact that the nucleus is net positive, okay, so it's not all positive, it's just net positive. And then they're trapped in a system where these electrons are in tension. They say this electron would want to get closer to the net positive nucleus, but the fact is the net positive nucleus has electrons in it somewhere. Okay, so that's going to be a problem. And these other electrons are obviously pushing it away. And that's the tension the electrons are stuck in atoms. The electrons are not orbiting, so it's just nonsense. And so what you can do is I could perturbate it, that is, I could hit it with a discrete force and jiggle it. But I can't really knock it out of this position, because it's still very attracted to this nucleus, and it's got to balance against these other electrons in the field. So there's a whole bunch of other electrons in the field, and it's got to balance against all of their distances and its attractive force. So if it's in a place, an electron has a place. That's a fact. They're not zooming all over the place and just doing whatever they want. They're actually literally shared. So when two atoms are stuck to each other, they're literally sharing the electron. Okay, the electron isn't going anywhere. It's stuck in that position between the two nucleuses. So anyway, that's where these arguments get difficult, because your submodel, your underlying unnotions, are just as bad as these later conclusions. You always have to go all the way back to the beginning. So if I could at least get you to just understand that there's a concept that the electron is jiggling, okay, that it's under a constant pressure between all of these external forces pulling and pushing on it, so to speak. And there's no pull, there's just the absence of a push. But anyway, and so this whole conversation is just about the fact that I can hit it with an energy, and it's enough to jiggle it, but it's not enough to knock it out. And the truth is, if you want to make electricity, you need to make the electron here jump, okay, to the next atom, and push that electron and force it to jump. And that's the cascade that is electricity. So that's how you create an ionization energy, which basically means you've given the photon enough energy to break it free. Now the idea is, if you could understand it's in this tension, you could understand that if I hit it this way and it moves this way, it's going to want to go back to where it was, because that's the position where it has all the forces are neutral to it. So it's going to go back. So you can understand that, well, if it's going to go back, then I have to, if I'm going to give it enough velocity to leave, I have to hit it more than once. I can't just hit it once. I got to give it more energy. So if I hit it twice, you can understand that if I have an interval between when I hit it that's as large as the interval of its return to its original position, I won't have gained anything. Okay, so if I hit it, it moves at a velocity, a higher velocity in this direction, but it stops and goes back. And then I hit it again, it stops and goes, okay, I'm not going to get anywhere. But if I hit it while it's still moving in this direction, and I hit it again, now I can give it more velocity. So the idea is if you have a series of atoms, and I hit an electron on this atom, right? So I hit it with some energy. It's going to push on the other electron. So now this electron's moving, and this, say if there was one over here, it would be moving, and this one's going to move over here, and this one's going to move over here. So I've pushed energy in. The other electrons have pushed out because I'm pushing energy in, pushing them out. Okay. And now if another piece of energy hits any one of these electrons, it's already got, say, 10 miles an hour. It had 0 here. Now it's going 10 miles an hour. So all of these are going 10 miles an hour. You can understand that now I'm going to give it another 10. So now it's going to be going 20 miles an hour. And then coincidentally, or by the circumstance, it just happens that now this electron gets hit again. All right, that's going to cause another expansion. So if I hit electrons or I hit atoms, any electron in the atom will do, and I pressurize the atom by doing that, then the cascade of pressure will keep moving. And the fact is that I'll hit one electron here, I'll hit a different electron here, and I'll hit a different electron here. But the fact is I'm going to change the pressure and keep increasing it. And so the fact is it's going to move faster because I've already pre-pressurized the atom. So I've put pressure into an atom. The atom next to it is now pressurized. Okay, not to the same pressure, but some half of it, let's just say. So it's going 5 miles an hour. Now I'm going to hit with another 10 mile an hour force. Now it's going to be going, now it's 15 pressure. It's going to share that with the atom next to it, so it'll be 7 if it's half. You see how I can just keep increasing the velocity eventually, and I'll make it go fast enough to break free of what's binding it. So, but it's just as simple as this argument. If I hit something and it's going 30, 20, 10, 0, obviously if I hit it quickly while it's still going 25, I can add a lot more velocity. And if I hit it again before it slows down, more velocity. So you can add velocity. So it's just a tipping point argument. If you want to tip something over, hit it quickly with 3 objects, it tips over. Hit it slowly, yeah, no, you don't get anywhere. So that's the photoelectric effect in particle form. Alright, back to the video. Yeah, we only got through 11 seconds. Well, something like that.
Such as arises in an incandescent light bulb. The classical prediction is that radiation intensity...
So there's no classical prediction that does any such thing. So nobody realistically could possibly think that there's infinitely fast motion is easy. Just as easy as really slow motion. Nobody would think that.
Always increase with frequency. Planck was able to derive a radiation law that matches what is observed.
We don't even know how well it does match, actually. So I've seen no evidence of a perfect match. But look, it's a pretty simple parabola. So obviously lots of things could be causing the effect.
Intensity reaches a peak at a certain frequency and then rapidly drops off at higher frequencies. But to achieve this, Planck...
So that you're just basically saying the cars, the electrons, can only be going a certain maximum speed. They're only going to be able to create frequencies of a certain maximum frequency. The electrons have a limited oscillating velocity.
Planck had to assume that radiated energy comes in discrete chunks, or quanta. At frequency nu, the quantum of energy is Planck's constant h times nu.
So that's all useless mush, in my opinion.
He called this assumption an act of desperation, and although it produced the correct formula, he was highly skeptical of it.
Well, good reason, I suppose. Because, yes, all it's really doing is creating a termination. It's just creating a mathematical mechanism that causes there to be a prevention of infinite progress.
The assumption worked because at a temperature T, there's an average thermal energy, kT, available to excite a radiation.
So we could just say if there was a bunch of cars from truck to Volkswagen, I guess people don't know what a Volkswagen is, so anyway, little car, big car, and there would be an average. But the point is that on either side of the average there will be events, and the point is it's more likely on the lower side of the average than the higher side of the average.
Radiation mode. Here K is called Boltzmann's constant. For low frequencies, the energy quantum is much less than kT. The mode can have an energy of...
So this mode thing is not a very good way of describing it. These lines equally spaced is not a very good way of explaining anything. So I just call bullshit.
kT, which is the classical prediction by containing some number of quanta. But at high enough frequencies, the energy quantum will be more than kT. These modes either have to...
So the whole idea of energy built into a photon is, my argument is, it's not really more energy. You're throwing baseballs, they move the speed of light. That's what a photon does. And all the real argument is if I throw the 3 baseballs really quickly in sequence, they're going to be capable of disturbing systems a lot more than if I throw the baseballs once a day. Okay, so if I have a huge period of time between when the baseballs hit something, they'll be less effective than if there's a very short period of time between when I throw the baseball. So again, it's just a tipping point argument. You will tip atoms if you provide the energy in a small amount of time. You can break things that way.
Have no energy, or more energy than on average is thermally available. So at higher frequencies, the probability becomes greater that a mode will have no energy at all.
So it doesn't even make any sense. At higher energies, it doesn't have any energy. But you know, what are you talking about? It's just, no, it's unlikely to happen. You can't. It's really hard to make an electron vibrate very quickly. Hard to do.
This is how the quantum hypothesis explains the drop-off of radiation intensity with increasing frequency. Planck's skepticism about the quantum hypothesis was understandable. Radiation takes the form of electromagnetic waves.
So whatever, radiation. It's not all forms of radiation, it's just photons. So again, and this whole idea of this oscillating field crapola doesn't say anything. It's not physical.
And the energy of a wave is distributed throughout space. How could this energy exist in discrete chunks? Discreteness is something we associate with particles.
All right, so there's just no point in having the conversation because, frankly, it's all nonsense. Obviously, laser beams are not frickin' waving anywhere. Obviously, you're just talking about a frequency of events. There's an event. Photons are an event. They're something that happens to an atom or some material object. It has to be of a substance to it. You could argue that the polarization of a photon is gigantic. It's 1,000 atoms of polarization. How could a single electron produce a photon? It's really not possible. So it's obviously a composite object, and it's just saying it's a number of pieces. Okay, I'd say 3 would be enough. 2 might be enough. Could be 10. But the point is that it's just a number of baseballs, and you're just saying, if I throw the 10 baseballs in this little amount of time, it can do more damage than if I throw the baseballs in a gigantic amount of time. And then the other argument is or I could throw 1,000,000 baseballs. So, see, you can just sit here and go through each one of these things and say, this is the better way to understand it. So let me just give you a really quick radio wave drawing, hopefully very quick. As I pointed out, it's so obvious with this whole antenna thing, right? So you have an antenna, so you know that the thing creating your photons, your radio signal, it has it has these rules, and you can simply understand that. Yes, all you're doing is putting an alternating current into the antenna, and that's all you're doing. All right, and so what you're doing is you're basically sending a signal. Now, as you know, the signal can't go any faster than the speed of light. It's going to be something less than, but some substantial speed up the antenna is how the atoms will expand. And so basically, you're going to be launching, let's say, ionizing energy. You're going to launch electrons off the surface. All right, they're not going to leave the surface because you didn't heat the thing first. Okay, but and so you cause a push of an electron into the system, and this push happens first, and then by the time this push happens, this push has gone this far. All right, and you can just understand. So the actual signal, okay, in space, if I was to look at the reflections from the vibrating electrons, that is, the electron gets hit with the electricity, pushes out. the next one pushes out, the next one pushes out, the next one pushes out at the speed of light. So this is the signal traveling through space. And it's made out of a gigantic number of little bits. So the photon is made out of, zillions of this, okay, just these compressions, where you've taken the field that exists, the energy, the heat, and you've compressed its frequency, you compressed it. So you have this blob of compression here, and you have a blob of compression here. And all of these distances are the same between them. So obviously, if any piece of this hits something, the frequency will still be there. You can, So it's just about the pieces hitting. So it doesn't have to hit the whole antenna. It could just, obviously it works better the more antenna you got. But it's just this idea that you're just going to hit the antenna in the same way the antenna produced the output, which was electrons pushed out. And now you're basically going to push in on the electrons in exactly the same sequence, in the sense you're going to hit one, then you're going to hit nearby with another piece, and then you're going to hit nearby with another piece. You're going to hit this sequentially onto the surface, cause the same cascade, the same push of an electron from one atom to the other atom to the next atom to the next atom. They're not high enough energy to leave the surface. It's not creating ions. Well, it's technically creating ions, but the ions are converted immediately into non-ions. But anyway, so you're just duplicating the effect. So the antenna pushes, and then the receiving antenna gets pushed at the same frequency. It's really not very complicated. Particles have no problem describing the circumstance. Alright, continuing.
Not waves. And nobody had ever seen direct evidence of any type of radiation particle. But then it was pointed out that such evidence had indeed been observed in a phenomenon called the photoelectric effect. A solid material contains electrons, and these could be pulled loose by supplying electrical energy, as applied in the form of light should also be able to...
Pulled loose. No. Pushed loose. So anyway, this is so funny. All right, so obviously this is just what I'm saying. This is just a matter of understanding that you have to increase the velocity of something in tension. And for the tipping point, it's gravity that's creating the tension and its center of gravity. And that's what you have to overcome. But I just mean it's the same argument, that if you hit it quickly, all of the velocity, almost all the increase in velocity is maintained or retained. And the slower you are about pushing it, the more you lose to the friction of its tension.
Remove electrons. But if a material is illuminated with low-frequency light, represented in red here, no electrons are ejected, even if the light is very intense. On the other hand, if the illumination is high-frequency light, represented here in blue,
and the higher the frequency, the more intense the ejection, indicating the more velocity you're retaining. So the faster you can throw your baseballs, the more the energy of those baseballs will be revealed in motion in one direction. It won't be absorbed by any kind of friction. So you could argue that the same law it evades friction in any surface. So if you want to plow through something, the faster you can get it going, the less any absorbing force from the sides can stick to it, so to speak, can pull any of its energy. So the less diffraction there is, the less of the energy goes in other directions, the faster you get it going. So the faster the motion, it defeats the friction.
Electrons are emitted, even if the light is very weak. It was Einstein who in 1905 explained this by considering Planck's quanta as particles moving at the speed of light.
So it's hard to figure out exactly what Einstein was saying, whether the photon was still a particle or whether the photon was made of energy quanta. But
now called photons. If W is the energy needed to remove an electron, only a photon with an energy greater than W can eject an electron. The total light energy, which represents the number of photons striking the material, will determine the number of electrons ejected, but not whether electrons are ejected. And the kinetic...
So that doesn't even make any sense. So obviously it won't determine if they're ejected if it's not a high enough frequency, so there won't be any number.
Energy of the ejected electrons will simply be the energy left over from this photon-electron process.
So this process of converting the energy, and again, the idea is you have a more efficient conversion, the faster you can make the event happen. So if you make the whole event happen over a shorter and shorter period of time, the sticking forces or the gravity or anything else to affect it will be less effective. So just like in the gravity argument, if I go through a gravitational field quickly, I defeat the field. It doesn't have any effect on me. So it's like spray paint argument. I got a constant spray of paint. The faster I go through the paint, the less the paint sticks to me, the less paint that I've been disturbed by. And that's the underlying argument here, is that all the adhesion forces that might keep something from moving are defeated by velocity. The higher the velocity, the less you lose to friction.
On the other hand, a photon of low-frequency light does not have enough energy to free an electron. So even if there are many such photons, that is, the light is very bright, no electrons will be ejected from the material. Thus, Einstein explained how Planck's quanta manifest themselves as, quote, real particles of light.
But it's missing the fundamental argument, which is why. So again, they'll draw this as saying the electron is in a hole and you need a certain amount of energy to pop it out of the hole. But that's not the actual argument. The actual argument is it's stuck. It's in glue. And if you hit it quickly, you can break the glue.
A more prosaic example is how photons explain sunburn and sunscreen.
So this is just the same argument, just saying that when do photons actually start ejecting electrons? So that's the point. So this is what's basically just called ionizing radiation. So there's just a certain point where you're hitting the surface with enough speed, that is in a short enough time, with your energy, and the system can't absorb it, and it breaks, and electrons are cast off.
If you look at the spectrum of solar radiation, you find that the great majority of the energy is in the visible and infrared regions. Only a tiny fraction is in the high-frequency, short-wavelength...
All right, so it's not a tiny fraction, really. If you look from the center where it starts to go down, we're getting closer and closer. So this is ionizing radiation is right there. It's not exactly nothing, it's like 10% of the total radiation. 7%.
Ultraviolet region. Yet sunscreen protects us from sunburn by blocking only this small amount of UV radiation. Let's assume the chemical reaction responsible for sunburn requires a certain energy W.
So this really isn't on the subject, but whatever, so it's fine. Look, they want to convert everything into some sort of mathematical notion. You're just basically saying that chemical reaction requires two atoms to hit each other with sufficient velocity to overcome the fact that the nucleuses don't like each other. And so again, you're trying to overcome the forces that'll be created that create resistance. And again, speed breaks the friction. So the faster you can get the atom moving, the deeper it can connect to another atom, and that means the more likely it is you're going to get over the fact that the surface electrons hate each other, and you're basically going to push through that hatred.
And light is composed of discrete photons. If a molecule absorbs a photon of energy less than W, there will be no chemical reaction and no sunburn. If a molecule absorbs a photon of energy greater than W, then there will be a chemical reaction, leading.
Obviously, a shared electron is a concept, so if you have a bunch of atoms and you're going to try to get two atoms to merge, one of the electrons has to be ejected. So you have to have enough energy to eject an electron to create an ion that'll connect to the other atom. And now they can share an electron. So that's basically the chemical reaction, is always just some form of creating an ion somewhere.
To sunburn. For sunburn, the required energy corresponds to photons with frequencies in the ultraviolet region of the spectrum. So by blocking only a tiny fraction of the sunlight's energy, our skin is protected.
So again, it's not ultraviolet. The X-rays are going to hurt you. All the other stuff that's also in that high frequency range is going to hurt you. The cosmic rays, the gamma rays, the whatever rays, they're all doing damage. They're doing lots of ionizing, even more, frankly. But there's a smaller number of them. So that's the good news. You're getting hit by X-rays all the time. There's background radiation. It's always hitting you.
Against sunburn. The great majority of the sunlight's energy still reaches our skin, but no single photon corresponding to these frequencies and wavelengths has enough energy to cause sunburn-inducing chemical changes.
So the key is the whole argument about diffraction, that you can find a substance or a material like the microwave, the door on your microwave with a bunch of little holes in it. What's it doing? It's breaking the microwaves. The microwaves are too big to get through the hole, so the signal, even though all of the little bits, most of them, are still going through that door, the little bits are not organized anymore in those frequencies because the frequency was polarized, as I drew before, like the radio thing. It needs to mean so you're breaking its polarization essentially, and by breaking the polarization, it's now invisible as a microwave frequency. So it can't do any ionizing because it hits you twice instead of 3 times. There's only enough to do part of the job. It can't do the complete job, and so it needs all 3 elements or all 4 elements, or it's not going to be a photon.
We've seen that there is strong evidence that light consists of discrete particles we call photons, having energies given by Planck's formula.
So again, I'd argue that polarizing film for light doesn't get hot. I mean, of course it gets some hot because it's somewhat opaque, but the majority of the light goes through it, even when it's making the light invisible. So if I put 2 films crosswise, all I'm doing is the microwave door thing again. I'm basically guaranteeing that all the photons have pieces broken off, scattered. And so there's no hope of them being in the right sequence to create a photon. Not no hope, but you have a lot less photons. You've created a whole bunch of pieces, and now and then the pieces will line up. But unless you arrange it so they'll line up, that is, you have vertical surfaces or some other kind of, that's why they're round. Round guarantees, if they put square holes in the door, it wouldn't work as well because the square holes would create surfaces where you'd end up with a fringe pattern. And the fringe pattern is 50-50. Half the photons are remade into visible photons. So you'd be remaking the microwaves, you broke them, and then you end up remaking them again. But a circle sort of guarantees you're not going to remake too many. That'll come up later in this video. A really good illustration of that.
But it had long been firmly established that light is a wave phenomenon.
So whatever. See, this is just such crap. Firmly established by edict and dogma. Not by evidence, not a preponderance of evidence, not even good reasoning applied to the evidence. Just a obnoxious invention of a Holy Ghost wavicle.
If you put a small pinhole in an opaque screen, place another screen to its right, and shine a beam of light from the left, then on the right screen, the light intensity will display a so-called diffraction pattern.
So we know it'll create a fringe pattern if you make the hole big enough. Yeah, if you make it really big, okay, then you're just stuck with the scatter of the light. and you'll see a round thing created. And again, if you make slits, and then you'll see the surfaces, and you'll get a fringe pattern. So we know it's not just a diffraction pattern. So why say this stuff that is just not true? If I make a very narrow slit, yes, I just get one blob because the two surfaces are too close to each other to create a wavelength of difference between them, and the only waves are coming off of the surfaces. So again, the light doesn't go through an opening and somehow spread magically. It goes through, and it is only the light that goes by a surface that can be bent. The light that goes through the middle isn't bent, and that's what you see. You see 95% of the light in a usual slit experiment, 95% of it's hitting that middle. It's not fringing at all. It's going straight through the opening. This is so annoying. It's just so inaccurate.
That is the unmistakable signature of a wave. If you open a second
it's just pathetic. It's not the signature.
pinhole, so that another diffraction pattern appears on the screen. A very rapid variation of it.
So he made the two lumps. So even though you have two holes that are a millimeter apart, you're casting it on a screen. You have some expectation that the two holes are going to create one is going to make a blob way over there, and one of them's going to make a blob way over there. No, it's not going to happen. It's going to be a millimeter apart. They're going to be right on top of each other, those two blobs. So again, they can't even get that right. And this drawing is of a single slit, because there's only two sources, and they don't even have the center maxima doubled, which it would be if these are open slits. But they're not open. So again, the assumption is this is an infinitesimally small slit, so you've destroyed two of the sources, and you won't have a central maxima then, a double central maxima. But it's just cheating.
Intensity.
I mean, you open those slits, and you're going to get the envelope pattern plus the double maxima.
Interference fringes will appear. These observations are a slam dunk for the wave.
So they're not. It's just such a distortion of the actual experiment, what it actually produces when you have actually open slits. It's just they're showing you one tiny narrow image of something happening. So they're showing you the webbed feet, and that's it. And then they're saying it's obviously a duck, that kind of bullshit.
The theory of light. Let's look at this experimentally.
So this is an interesting version of the double slit. So two holes poked in some surface of different sizes, and then you project them, shine light behind it, and project those two, and then you move it further and further, enlarging the image. And you start to see things that were invisible.
First, we take an image immediately after the pinhole screen. This shows light emerging from the two pinholes, one large and one small.
Pretty big distance apart. So we're talking about many diameters of the actual opening of one of the pinholes. So a number of, maybe it's 7-8 times the diameter of the opening is the distance between them.
Next, we take an image some distance away from the pinholes. Here we see that the light from the pinholes is spread out into ring diffraction patterns.
Right, and the rings are created by the surfaces, right? See, you don't have a straight edge, so now all the edges are, at least little surfaces, and they're all making the pattern in that orientation. And so it's really the same thing. I mean, you could draw a straight line through that image, but that's the only point where there's actually a double slit, because if I change the orientation on either one of those, there's no other point sources. So you'll see it. It's a key feature here. I'll probably have to draw this.
Notice how the rings for the large hole are more closely spaced than are the small hole rings. These features are precisely explained by the wave.
Right, and it's not precisely explained by the wave theory. The wave theory doesn't explain why that's true, that the big opening has smaller bars than the small opening. It doesn't explain any of that. It's the same frequency light coming in. It should be the same size, blah, 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 blah. And the truth is that it's completely dependent on the fact that you're really just creating two sources on either side of the circle. So as you go around the circle, you have two sources, two sources, two sources, two sources. So in that line is where you're getting your fringe pattern. So on every single possible line through the center of the hole, you can understand there's a fringe pattern, because there's two sources on either side of the center. Two sources, two sources, two sources. It's always about the surfaces. That's what's made clear.
Wave theory of light. Moving even farther away from the pinholes, the ring patterns grow in size and overlap more. And looking at this in more detail, we see closely spaced vertical lines.
So I'm not going to try to make that bigger. So through the whole image here, they're mostly vertical. I mean, some of them are a little bit this way, a little bit this way. Not perfect, but they're mostly vertical. And what is that being caused by? Well, the simple explanation is, yeah, I'll use my arrow. Safer than the mouse. Yeah, safer, I think. All right, so arrow, do your job. All right, first notice that the white, where there's light plus light, it doesn't make a dark, right? It's supposed to make a dark, by their theory. So the only place that these stripes happen where the extra source creates a difference is the extra source is making a light spot on the dark spots, but there's no making a dark spot on the light spots. So you can't really see these little tiny vertical lines, but yes, there's just vertical lines going all the way through the whole pattern this way. Why are they doing that? Well, because the only direction through both of these centers is right here. So essentially that's a slit experiment in the sense that the horizontal is the only, see, I can't go through this center. Whoops, I don't get a second one. I can't go this way and get four sources. I can't go some other vector and get four sources. The only way I can get four, that is a surface, then a surface, then a surface, then a surface, is through this one line. So this dimension from the very outside of the small hole and the very outside of the big hole, that's the dimension that's creating the little lines. And the little lines are infinitesimally small compared to these rings, right? So the little lines are probably hundreds of times smaller than the ring size. And so obviously that distance must be hundreds of times bigger, right? And that's what I was pointing out in the beginning. The two holes are very far apart. So it's a very huge amount of distance between the outside edge of the small hole and the outside edge of the big hole. That dimension is gigantic, which means obviously lots of wavelengths, okay, fit inside of it, meaning the little dots are much, much tinier. And that's what these little stripes are being created. And that's why they're all vertical, because there's only one dimension where that's possible. They have to be vertical because the only alignment where all four surfaces are in the picture, the only alignment is that horizontal alignment. So that's why all the stripes are vertical, because it's basically duplicating the double slit in that one dimension. So I thought that was really quite interesting. It's a great reveal in the sense that it's showing you exactly, these little lines are exactly proportional. If you counted them, you could know exactly how far apart the two openings were. All right.
Superimposed on the diffraction patterns. These are interference fringes. And there's no reasonable way to explain these.
Yes, there is. There's just surfaces. And the surfaces disturb the photons, scatter their pieces, and the pieces have a 50-50 chance of being put back together. And again, critical to understanding that is the surface isn't made of flat steel. The surface isn't a flat thing. The surface is covered in electrons. And on every surface, what are those electrons doing? They're reacting to the internal energy or heat inside the object, and they're just moving in and out. They move in this direction. They don't move some other direction. They move in and out of a surface. So what are they doing? Photons comes in this way, photon gets deflected this way, gets deflected that way. And I don't mean the whole photon. I'm just saying the pieces that make up the photon get scattered. That explanation works just fine. It actually works perfect because it shows you that it's the two-slit experiment is the four-surface experiment. The surfaces cause all the fringe light. Make the openings very big and you get a whole bunch of bright light in the center. Make the slits very small, you don't get the bright center.
Observations without invoking the concept of waves.
Now, it's just wrong. They never even tried. And this is just part of their Catholicism. It's just another religion. They just dogmatically tell you you must believe and screw actual evidence.
We think of a particle as a little thing at a single point in space, possibly moving in some direction at some velocity. And we think
so we know all the forces move at the same velocity. So we know gravity, magnetism, electricity, and light all move substantially. They're all limited by this speed of light thing, and they're all can approach that speed. So we know the forces, the stuff giving matter motion, that's moving the speed of light, and the matter moves something less than the speed of light.
A wave is something spread out in space.
There's Sisyphuses and there's boulders. We see boulders move. We don't see the Sisyphuses that are pushing them.
Oscillating with some frequency. If light is so precise...
And we certainly don't see the Sisyphuses that aren't pushing a boulder. The force is just a million times, smaller than the stuff we can't even see, the electrons. So obviously we have to infer the motion is being caused. And the simple explanation is the force is eternal. It never stops. The Sisyphuses live forever, and the material boulders live forever. And all you're really saying is Sisyphus push, Sisyphus stops pushing. It's free energy versus energy pushing matter. And that's the two states the universe can be in.
Nicely described as a wave, but also displays unmistakable particle properties. Then what is it?
So it is mistakable. So you did make the mistake. So it's wrong to say that those properties even exist, let alone are substantial enough evidence to defeat this simple argument that it has every appearance of being a universe of reliable function. And the fact is the energy rationally behaves. It doesn't irrationally behave.
Exactly. What is a photon? How do we picture it? The answer is not very well. We can draw.
Not at all. So again, this silly idea that there's some field oscillating and pushing things around and causing all this it can't be more complex than the world we exist in. It has to be simpler. You can't do this, make the physics of the elemental universe more complicated than the physics we actually engage in. And so obviously that squiggly line isn't saying anything rational or reasonable. And then if they're really going to be true to it, they have to put this second line, for their 1 million times weaker magnetic field. And it's just ridiculous nonsense. It's just a frequency. It's a dot in space, and then another dot in space, and another dot in space. That's all it is. And if you want to be more technically precise, it's a dot in space here going on a horizontal vector, and a dot here, a horizontal vector, and a dot here on a horizontal vector. It has a frequency and a polarization.
Draw a little wiggle indicating a wave-like oscillation with an arrow indicating a particle-like thing moving in some direction. But the fact is, we simply don't have any day-to-day experience with something that has the properties of both a wave and a particle. So we don't have a frame of reference.
So the point is we can model it and analogize it. And so I'm saying that my tipping point analogy with baseballs works just fine. The analogy of the electron being the car and the force being something much, much lighter, and the fact that the electron can push on the force, that works to an extent. You can't change the speed of the force, but you're changing when it reflects. The idea, look, this simple argument that if I had a field of energy I existed in, and there was a certain number of things that were going to hit this hand here, and I move the hand forward, it means I have changed when all those reflections are going to happen. And obviously, all those reflections would have been, if my hand stayed back here, they would have been this far apart. And if I move my hand here, now all the reflections are this far apart. Duh. I can increase the frequency of the energy hitting something if I push into that frequency. And then if I move away from it, I obviously expand the distance. So the energy comes in with a total distance of this, and if my hand's moving away, that's the total distance of this.
In which to understand such a thing in any intuitive sense. We've seen images that clearly show the wave nature of...
So it doesn't do any of that. It breaks its own rules, and it's clearly understandable that these are surfaces. You can see the surfaces are the thing being illuminated. You're seeing the surfaces. It's a pattern of the surfaces. It's an image of the surfaces. Obviously, the surfaces are creating all of these effects. And none of them are being created by a photon that went right straight through the middle of the opening. Those photons are right in the middle where all the white is. They didn't do anything. They didn't fringe. They didn't break. They didn't do anything. They went straight through and hit the surface. This has nothing to do with going through an opening. This has everything to do with going by surfaces. And yes, you need two contributors. If I just have one surface, and I shoot light, well, I just broke the photons. I can't put them back together because I don't have another source to send other broken pieces. So I can't, if I don't have a second source, I can't do any reconstruction.
Light. We've also presented evidence that argues for the particle nature of light, but we haven't actually seen light particles with our own eyes. So, reasonably, we might still be skeptical about that.
Now, that would be unreasonable of you to expect to be able to see something that you can't see, because we only see something by bouncing something off of it. And obviously, if it's the smallest thing in the universe, I have nothing I can bounce off of it that's smaller than it. So I have no hope of seeing it. Okay? So we are always stuck just trying to model it rationally. And I would just argue that this notion that they somehow have proven waviness and completely destroyed notions of particleness is just bullshit. And smashing the two together and saying it's, a waving particle. Now, it might be possible to say it's particles that look like they're in a wave. So you could say a wave of soldiers, and you'd know that they're individual soldiers. They aren't tied to each other with ropes. And the fact is they're obeying, each individual soldier's obeying the law of physics, and they all end up looking like they're organized. But they don't have to be. You start them all with the same energy, they go the same distance in the same time. Looks like a wave, but it isn't.
especially since the implications are a bit mind-bending. Fair enough. What if we repeat the pinhole experiment, but with light so weak that at any given time there should be no more than a single photon in the system?
So this is another one of the giant canards. Maybe I'll just stop it here and just say this experiment's a lie. All right, single photons. They create single photons by doing this again. They put a bunch of dirty glass in the way of the light. And the dirty glass is just surfaces. It's little particles suspended in the glass that block the light. So it goes around the surfaces, fringes all over the place. So you're creating a huge number of broken photons. So it's not that there's no photons in the experiment. There's a ton of them. And you just need something to reconstruct them. You just need some mechanism to make it possible for them to hit two surfaces, okay, and send a constituent to a location and turn it back into a photon. So, it's just bullshit though when they say single photon experiment. There's no such thing as a single photon experiment. There's no such thing as creating a single photon is like creating 1 unit of electricity. It's not possible. We don't have that technology. All right. So anyway, so I'll probably come back to this, with a part 2. This second half is not that interesting because it gets into some kind of wooey crap, as I remember. But I don't remember what exactly it was. Oh, it does that whole, 3-dimensional drawing of the vectors of the magnetic field's doing this and the electric field's doing this, and that kind of nonsense, which is just a waste of time. Anyway, we'll see how it goes. So, till the next time and such, and so forth and whatnot. So anyway, this is just they're all canards. Kinetic energy is nonsense. Madame Charlet's experiments were nonsense. Really bad physics. Levers do conserve momentum. Pulleys do conserve momentum. They do not conserve kinetic energy. Kinetic energy doesn't move rockets. I mean, it's all over the place. It's nonsense physics. And this stupid wave-particle duality is just the next step in a fake, phony, fraud physics. You're not, especially in the kinetic energy sense, because they start talking about photons having kinetic energy. And no, all they have is momentum. And it's just so wrong to associate. And again, this is because frequency, the whole idea that they turned frequency and said it has more energy. When again, if I throw 3 baseballs and they hit the surface, ... that is going to be more effective at breaking the surface than if I throw the baseballs ... That's less likely to break it. That doesn't mean they has more energy. It means that you applied the energy in a manner that broke the system that was held together, but it didn't have more energy. It took advantage of a loophole. You can defeat friction with velocity. That loophole. All right, till the next time and such and so forth and whatnot.